That screen you're looking at right now is the result of thousands of years of human ingenuity. Today, we're going to pull back the curtain on the fascinating and surprisingly long story of the computer.
You know, it can often feel like magic, right? But believe it or not, it all starts with a very simple idea, an idea that's actually thousands of years old.
So, how in the world did we get from these simple beads on a frame, to this, a complex machine of circuits and code? It's a huge leap for sure, but the whole story really starts with one simple core idea. To really understand that whole journey, we first need to get to the heart of what a computer actually is. And thankfully, the name itself gives us a pretty big clue.
At its very heart, when you strip everything else away, a computer is simply a machine that's designed to calculate things. That was its original and most essential purpose. And here's the thing. Every single computer, from the oldest mechanical gizmos to the smartphone in your pocket, really only does three basic things. It takes in some information, it does something with that information, and then it gives you a result. We call that input, process, and output.
Now, this whole idea of a calculating machine, well, it's not new, not by a long shot. In fact, to find its origins, we have to go back thousands of years, way before electricity was even a thought.
Our story really gets going with tools just like this, the abacus. Developed about 5,000 years ago, a lot of people actually consider this to be the world's very first computer, a totally manual tool for doing basic math.
So for centuries after that, you had these brilliant minds just building on that one simple idea. We started seeing mechanical calculators with all these intricate gears and levers, and even incredible steam-powered engines designed by Charles Babbage. These machines just kept getting more and more complex, learning to do more than just add and subtract, but to actually follow a basic set of instructions.
Okay, but the real revolution, the one that kicks off the journey to the device we're on right now, that all started in the 20th century. This is where we see the birth of electronic computers, and they've evolved in 5 really distinct stages, or what we call generations.
All right, Generation 1. It was all about one key component, the vacuum tube. It kind of looked like a light bulb, and its job was to control and amplify electronic signals, basically acting like a switch.
And when I say these early computers were big, I mean it is almost hard to wrap your head around. Machines like the famous ENIAC were just massive, weighing 30 tons, filling up entire rooms, and getting so hot they needed their own custom cooling systems. And on top of all that, they were really unreliable. Then, a tiny little invention called the transistor came along and changed absolutely everything. This was a real game changer. See, a transistor did the exact same job as one of those big, clunky vacuum tubes, but it was tiny, way faster, and so much more reliable. It used way less power and didn't burn out all the time. This one little invention was the key that unlocked smaller, more powerful, and eventually more affordable computers for everyone. So, things were already getting smaller and faster, right? Well, the third generation took that idea and just ran with it. Instead of using separate transistors, engineers figured out how to cram lots of them onto one single tiny piece of silicon. This was the integrated circuit, or what we just call a chip. And it didn't stop there. The miniaturization just kept going. Pretty soon, engineers figured out how to put the entire brain of the computer, the CPU, onto a single chip. This was the birth of the microprocessor, the exact technology that lets you have a super powerful computer on your desk or even in your pocket.
And that brings us to today, the 5th generation. This era is all about artificial intelligence. We're now designing computers that can actually learn from data, reason through problems, and talk with us in ways that feel much more natural, much more human.
So when you look at it all laid out like this, you can see this incredible pattern, can't you? With every single generation, the technology got smaller, the speed got faster, and the machines got way more reliable. It's just an amazing story of constant improvement.
Okay, so we've seen this incredible journey of technology getting smaller and more powerful. But here's the really cool part. All of this technology, from the oldest to the newest, still runs on that same super simple 3-step process we mentioned at the very beginning. So how does that actually work?
It really is this simple. Everything follows this basic flow. You provide some kind of input, like clicking a mouse or typing on a keyboard. The computer processes it, and then it delivers an output, like a letter appearing on your screen.
Let's make this real for a second. Just take a moment and think about the last time you used a calculator, maybe on your phone. The numbers you typed in, that was the input. The actual math it did, that was the process. And the answer that popped up on the screen? Yep, that was the output. It's the exact same simple pattern, it's just happening millions of times a second inside our modern devices.
And that thinking part, the processing? Well, that's all handled by one crucial component, the Central Processing Unit, or CPU. You can think of it as the brain of the whole operation, the part that carries out every single instruction.
You know, when you step back and look at the big picture, the progress we've made across those 5 generations is just mind-boggling. The scale of it is almost hard to comprehend.
This right here really puts it all into perspective. What once filled an entire room and weighed as much as several cars can now literally fit in the palm of your hand. We've gone from 18,000 fragile vacuum tubes to millions or even billions of tiny transistors on a single chip.
Yeah, this quote on the screen pretty much says it all, doesn't it? From those ancient beads all the way to modern microchips, the goal has always been the exact same: make our calculations smaller, faster, and more powerful.
So no matter how complicated it seems, just remember this. Everything a computer does, from playing a movie to guiding a spacecraft, just boils down to that one fundamental rule: input, process, output.
So now you know the story of the idea behind the computer, how it all came to be. The question is, what will you explore next about the machine itself?
You know, have you ever stopped to think about what's really going on inside that black box sitting on your desk? We use them every single day, but let's be honest, how they work can feel like total magic. Well, in this explainer, we're going to pull back the curtain and find out how they actually work, step by step. Think about it. It's something we do hundreds, maybe thousands of times a day without a second thought. You press a key and boom, a letter appears on your screen. It feels instant, right? But underneath that simple action, there's a really fascinating and logical process going on. So let's explore that together. To really get how a computer works, we need to start with one super simple core idea. When you boil it all down, a computer has one main job: to be a processor for data. So what does that even mean, a data processor? Well, it's just a device that takes in all sorts of raw facts and figures, we call that data, and then it follows a set of instructions to turn all that raw stuff into something useful, something meaningful. And that we call information. This little diagram shows that perfectly. You've got data going in. That could be anything from you clicking your mouse to typing a letter. The computer then processes it, and what you get out on the other side is useful information, like a finished document or a picture you can see. Input, process, output. That's the fundamental loop of everything a computer does. Now, the part of the computer that handles all this processing work, that's the Central Processing Unit, or the CPU for short. And honestly, the easiest way to think about the CPU is to just think of it as the brain of the whole operation. Okay, so if the CPU is the brain, what's actually going on inside of it? Let's take a look under the hood and see what this electronic brain really does. Think of this as kind of a computer's nervous system. You've got your input devices like your keyboard, your output devices like your monitor, and storage like your hard drive. But right there in the middle, connecting everything, is this CPU. It's the command center that directs all the traffic. But here's the thing. The CPU isn't just one big single part. To handle all of its jobs really efficiently, it's actually split into two specialized parts that work together perfectly as a team. So these two main parts are the control unit, or CU, and the arithmetic and logic unit, or ALU. Think of the control unit as the director or the traffic cop. Its job is to grab instructions and coordinate everything. Then you have the ALU. This is the calculator. It's the part that does all the heavy lifting with math and makes logical decisions. All right, so we have a director and a calculator. That makes sense, but how does a device made of silicon and wires actually think? How does it know what instructions it's supposed to follow? I mean, the CPU can't understand English or any other human language. It needs its instructions delivered in a language that it's built to process. So what language does this electronic brain speak? It speaks a language called binary, and it's actually incredibly simple because it's only made up of two symbols, 0 and 1. Since computers are electronic, this is a perfect system. You can just think of a 0 as an electrical switch that's turned off, and a 1 as that same switch being turned on. Now, just take a moment to really let that sink in. Every single thing you see and do on a computer, every photo, every song you listen to, every website you visit. It's all ultimately just a massive, incredibly complex pattern of these simple on and off states. Billions and billions of zeros and ones.
So how do we get from the letters we type on a keyboard to the ones and zeros that a computer actually understands? Well, it all comes down to a translation step. Let's see how our world gets translated into binary. For a computer to understand us, everything we give it needs to be converted. To do this, computers use a standardized code. It's kind of like a translation dictionary that gives a unique number to every single letter, symbol, and character we use. A classic example of this is a code called ASCII. As you can see, the capital letter A is assigned its own specific binary pattern. B has its own unique pattern, C has another, and so on for every character. So when you press a key, the keyboard sends that specific binary code straight to the CPU. Okay, so now we have all the pieces, right? We have the brain, we have its special language, and we have the translation code. Let's put it all together now and follow the journey of one single command from start to finish. This whole process is called the instruction cycle, and it happens millions, sometimes billions of times every second. It's got 4 steps. First is fetch. The control unit grabs an instruction from the computer's memory. Second is decode. The control unit figures out what that instruction actually means. Third is execute. The instruction is sent over to the ALU, the calculator, to do the actual work. And finally, step 4 is write back. The result of that calculation is stored back in memory, ready to be used. Fetch, decode, execute, write back, over and over and over again.
So, after going through the CPU, binary, and that whole instruction cycle, what's the one crucial point you should really take away from all of this? It really comes down to this. A computer is a processor with a brain, the CPU, that follows a long list of instructions by speaking a very simple language of on and off switches called binary. That is the foundation of everything a computer can do. What's really wild is that everything else, from incredible video games to artificial intelligence, is all built on top of this simple on and off foundation. It really leaves you with a final thought, doesn't it? What else is built on this simple language? The answer is pretty much our entire modern world. Today, we're going to pull back the curtain on one of the most important parts of your computer, its memory. It's really the secret to how your machine juggles everything you ask it to do, and it all boils down to a really clever compromise. Have you ever been there? You're in the middle of something important, and your computer just starts to crawl, even though you know it's got a super fast processor inside. It's frustrating, right? Well, the problem usually isn't the computer's brain, it's the workspace it has to use. Okay, so to really get why that workspace is so critical, let's think about the computer in a really simple, almost human way. It's all about a brain and the space it has to do its work. This really breaks it down perfectly. You've got the central processing unit, the CPU. That's the brain. It does all the thinking, all the calculating, all the heavy lifting. But it can't do any of that in a vacuum. It needs information to work with, and that information is stored in the memory unit. That's its workspace. And that leads us to a really simple but powerful truth. You could have the fastest brain on the planet, but if it has to get up and walk down a super long hallway every single time it needs a piece of paper, well, the whole process is going to be incredibly slow. At the end of the day, your computer speed really depends on how fast that brain can get to its workspace. So this is where things get interesting, because it turns out there isn't just one kind of memory. There are 2 main types, and they force a fundamental trade-off, a choice between speed, size, and of course, cost. First up, we've got primary memory. Now, the best way to picture this is like a small, perfectly clean workbench sitting right next to you. Anything you put on it, you can grab instantly. It is incredibly fast. But because it's such prime real estate, it's also kind of small, and it's expensive. And then, on the complete other end of the spectrum, you have secondary memory. This is like a giant library, or maybe a warehouse packed with filing cabinets. It can store a mind-boggling amount of information for a very low cost. The catch? If the CPU needs something from here, it has to put in a request and then wait for it to be fetched. It's much, much slower. So here's that trade-off in a nutshell. Primary memory gives you blistering speed, but you get less space and it costs more. Secondary memory is the exact opposite. You get a massive amount of storage for super cheap, but you have to sacrifice all that speed. You can see the dilemma, right? You can't just pick one. You really need the benefits of both. And there's one more absolutely crucial difference we need to talk about: volatility. Primary memory is volatile. Think of it like a thought in your head. The second the power goes off, poof, The information is just gone. Secondary memory, on the other hand, is non-volatile. It's like a note you've written down on a piece of paper. Even if the lights go out, that information is still there when you come back. Okay, let's make this real for a second. Just take a moment and think about the apps you have open on your computer right now. Your web browser, your music, that document you're working on. All of it is loaded up and sitting on that fast, temporary workbench. It's all living in your computer's primary memory, which you probably just know as RAM. So if you can't have one single type of memory that's both massive and lightning fast, what do? What's the solution? Well, computer engineers came up with a truly elegant one. Don't choose. Instead, you build a team. And that solution is called the memory hierarchy. Instead of trying to rely on one type of memory, computers use several different layers, all organized like a pyramid. This whole structure is designed to give the CPU the best of both worlds, to give it the feeling of a gigantic, super fast memory, but without the impossible price tag. So here's how that team is structured. Right at the very top, you have CPU registers. This is the absolute fastest, but also the tiniest memory, and it's located right inside the brain itself. Just below that is cache memory, which is a small, high-speed buffer that smartly guesses what the CPU is going to need next and keeps it ready. Then you've got our main workbench, the main memory, or RAM. And way down at the bottom is secondary storage, that massive library, like your hard drive, where everything is kept for the long haul. So let's take a quick look at how this team of specialists actually works together to make your computer feel quick and responsive. You're actually already super familiar with the players at the bottom of this hierarchy. We're talking about things like hard disk drives, CD-ROMs and DVDs, and of course, pen drives. This is that permanent, non-volatile library where all your files, your apps, and your operating system live. A simple USB pen drive is a perfect, everyday example of this. It's non-volatile, right? Your files don't just vanish when you unplug it. It's a reliable, portable little piece of that huge secondary storage library. The source material for this explainer puts it perfectly. The overall goal of memory hierarchy is to obtain the highest possible access speed while minimizing the total cost of the memory system. You see, it's as much an economic solution as it is a technical one. It's about getting the most bang for your buck. And the result of this beautifully coordinated system, it creates this incredible illusion. It makes the computer feel as if it has one single, gigantic memory that is also incredibly fast. By cleverly shuffling data between the layers, the system makes sure that whatever the CPU needs next is almost always waiting for it in the fastest possible spot. So, the single most important thing to take away from all this is that your computer's memory isn't just one thing. It's a team, a carefully balanced team of specialists, where each member plays a vital role in managing that constant trade-off between speed, size, and cost. So I'll just leave you with this final thought. The next time your computer starts feeling sluggish, when you have way too many tabs open, think about this hierarchy. Which specialist on the team do you think is struggling to keep up? Is it a cluttered workbench, or is the brain just having to make too many long trips to the library? Talking to a computer can feel like magic sometimes, but really, at its core, it's just a simple conversation. So today, we're going to pull back the curtain and break down exactly how that back and forth really works. It's something we do all the time, right? Almost without even thinking about it. You have an idea or maybe a question, and somehow this machine in front of you just gets it. But have you ever paused and wondered what's actually happening in that moment? The easiest way to wrap your head around it is to think of it just like a conversation. It's a two-way street. You say something to the computer, and then the computer says something back to you. The whole entire process really boils down to two simple ideas: input and output. All right, so let's start with the first half of that conversation. How you talk to the computer. This is all about giving it instructions so it knows what you want it to do. Here it is, laid out, plain and simple. Input is you talking. It's any information you send into the computer. And output, that's the computer talking back. Anything the system sends back out to you. Simple, right? Pretty much every single thing you do on a computer follows this basic pattern. And the way we do this, we use something called an input device. Think of these as little translators. Their only job is to take what we do, like a click of a button or a press of a key, and turn it into a language the computer can actually understand. And of course, these two. They're kind of the rock stars of the input world. The keyboard lets us type out our thoughts word for word. And the mouse, it gives us a way to point, to click, to move things around. For most of us, these are the main ways we speak to our computers every day. But, this conversation goes way beyond just typing and clicking. We use joysticks for gaming, scanners to get pictures into the computer, and microphones to capture our voice. Even just touching a screen or scanning a barcode at the grocery store, that's input. They're all just different ways of talking to a computer. Let's try a little something. Just take a moment and look around you right now. Your phone, it's got a touchscreen, a microphone. Your TV remote sends signals, maybe even the buttons on your microwave. You're actually surrounded by these little conversations all day long. Okay, so we've covered our side of the story. Now let's flip it around and look at how the computer talks back to us. This is the output. This is where the machine shows us the results of its work. An output device is basically the flip side of the coin. It takes all that processed information from inside the computer and translates it back into a form we can understand, something we can see or hear or even hold in our hands. It's how the computer replies. Now, the most common output device by far is the monitor, the screen. You could almost say it's the face of the computer. It's where the conversation becomes visible, showing us everything from plain text to incredible videos, and letting us see the computer's response instantly. It's pretty wild to think about how much that face has changed over the years. We went from those huge, boxy CRT monitors that took up half your desk to these super thin, sleek screens we have today. And it's not just about looks. Today's screens are sharper, they use way less power, and thankfully, they give us a lot more room to work with. But what if you need the computer's response in a form you can actually hold? Well, that's where the printer comes in. It takes that digital information and creates what we call a hard copy, turning the computer's output into a real document you can file away or take with you. And just like with input, output isn't just about what you see. Speakers give us sound, music, notifications, all that stuff. Projectors can take an image and blast it onto a wall for a whole room to see. And then you have these super specialized tools, like plotters, that architects use to draw out massive, precise blueprints. So, let's bring it all together. We've looked at how we talk to the computer and how it talks back. Now we can see the whole conversation, the full circle. So if you ever hear someone talk about I/O devices, which is just short for input-output, you'll know exactly what they mean. It's just the name for all the tools that make this conversation happen. They're the bridge between our world and the digital world inside that machine. And this is really the key thing to remember. A computer's processor might be incredibly fast and powerful, but without these devices to get information in and out, it's just a silent box. I/O is what turns it from a calculator into a tool we can actually use. One source we looked at put it perfectly. It said these devices are what allow the computer system to interact with the outside world. I love that. In a way, they're kind of like the computer's senses, its voice, its ears, and its eyes. So the main takeaway here is really simple. Input and output are just the two sides of a conversation we're having all the time. Now that you've got that down, it's kind of fun to think about what's next, right? How will this conversation evolve? Will it be more through our voices, maybe with gestures? The one thing we know for sure is that this conversation is always changing.
Hello, and welcome. Today, we're going to pull back the curtain on the personal computer. Our goal here is pretty simple: to make the technology you use every single day feel less like a mystery and more like a tool that you actually understand.
Have you ever felt kind of lost in a sea of computer jargon? Words like RAM, CPU, operating systems. It can all feel a little intimidating, for sure. But don't worry, the basic ideas behind it all are actually pretty simple once you break them down. All right, so let's start at the very beginning. What is a personal computer, or a PC really? Let's dig into what it's all about. When you get right down to it, a personal computer is just a super versatile tool. It's made for, personal use, right? It helps us with a ton of different things every day. I mean, everything from writing an email or doing homework to running a business, or even just kicking back to watch a movie. It's a real do-it-all kind of machine.
Okay, so when we say PC, it's not just talking about one single type of computer. It's really more like a family of different devices. And you're probably already super familiar with most of them, so let's go ahead and meet the family. First up, we've got the classic desktop computer. The name kind of gives it away, right? It's designed to sit on a desk and pretty much stay in one spot. This is that reliable workhorse you see in offices, schools, and homes all over the place.
And then, of course, there's the laptop. The biggest deal with a laptop is its portability. Everything's packed in a one foldable unit. It has its own battery. It's basically designed to be your digital sidekick, whether you're at a coffee shop or sitting in a lecture.
Now, a close cousin to the laptop is something called a netbook. These are even smaller and lighter, which makes them super easy to just toss in a bag and go. They're not meant for heavy-duty stuff. They're perfect for more basic things like browsing the web, checking email, or typing up a quick note.
And last but not least, the tablet. This is a much more modern take, right? It gets rid of the physical keyboard and mouse for most things and instead relies completely on a touchscreen. It's just this simple slate that you hold, and it feels really direct and intuitive when you use it.
So just for a second, take a moment to think. Which of these do you find yourself using every day? Is it a desktop, a laptop, maybe a tablet? Just recognizing them in your own life is a really great first step to understanding how they all work.
Okay, so now that we know the different types of PCs out there, let's take a look inside. We're going to start with the physical stuff, the parts you can actually see and touch. In the computer world, we call this hardware. Probably the easiest way to think about a computer is to imagine it has two sides, kind of like a person. You've got the hardware, which is like the body, all the physical parts. And then you have the software, which is like the mind. It's the set of instructions that tells the body what to do.
So, just to be super clear, hardware is all the physical components of a computer system. We're talking about everything from the monitor you're looking at right now and the keyboard you type on, all the way to the complicated circuits and chips that are hidden away inside the case.
And right at the heart of all those internal parts is the motherboard. A good way to think of it is like the computer's skeleton. It's this main circuit board that connects everything together. It's what allows all those different pieces to talk to each other and work as a team.
Okay, so we've talked about the body. Now let's talk about the mind, the other half of the puzzle, the software. It's that invisible force, the ghost in the machine, that tells all that physical hardware what to do.
So what is software? Well, it's basically just a set of instructions. It's the programs and the code that tell the hardware what to do, one step at a time. I mean, without software, your computer would just be a pretty useless box of electronics.
And the single most important piece of software on any computer is its operating system, or OS for short. Think of the OS as the main boss or the manager of the whole operation. It's the go-between for you and the computer's hardware. It manages everything, the memory, the files, all of it. And it's what makes the computer something we can actually use.
Whew! We've actually covered a good bit of ground here, from the different types of computers to what's going on inside. So let's take a second to pull it all together and recap the big picture.
So what are the key takeaways here? First, a PC is just a general-purpose computer for your own personal use. Second, it comes in lots of different forms, like desktops, laptops, and tablets. It's made of physical parts we call hardware, and it's run by instructions we call software. And finally, the operating system is the manager that makes sure everything works together.
And there you have it. You now understand the absolute basics, the difference between a laptop and a tablet, and that huge difference between hardware and software. Honestly, understanding this stuff is the very first step to feeling more confident and in control of the digital world around you. And from here, that world is really yours to explore.